Hello everybody. Thanks, Richard, for accepting our invitation to talk here today. Richard is an assistant professor at EPFL in Switzerland and PI of DRC starting grant IPSTARS that targets a 1% measurement of each knot using pulsating stars. Richard got his PhD at the University of Geneva, working on observational and theoretical aspects of Cepheids in the Gaia group. After that, he got a Swiss postdoc fellowship at Johns Hopkins with Adam Rees, where he began focusing on distance ladder. And finally, he got an ESO fellowship in Garking to work on physics and distance application of Cepheids. Today, Richard will present towards a direct 1% measurement of the Hubble constant using standard candles. You can start, please, when you're ready.
Thank you very much, Eleonora, and thank you all very much for being here today. It's a pleasure to also get an opportunity to present some of the work that we've been up to in my team. And while there's only my name currently on the first slide here, this is, of course, a team effort, and I will highlight in particular the people who contribute on the specific slides. And yeah, let's get right to it. So the title is, of course, using standard candles to measure the Hubble constant, and today's talk is really about how we can make the best of the information that is provided to us by stars that calibrate the base rungs of the distance ladder. And so, as a quick reminder, what do we mean by standard candles? Well, a standard candle, in a very basic sense, is simply an object whose luminosity you can calibrate in order to measure luminosity distances by the inverse square law of the way that the flux decreases over distance. So what you need in order to use a standard candle is simply to have an object that you can recognize to be the same as at large distances, to be the same as what you can calibrate locally, and then you can use these standard candles to measure distances. So there's a bunch of different types of standard candles, and in particular here I will focus on stellar standard candles, and I would like to make one main distinction in the types of objects that we can have, and one I would say we can group under the hat of individual standard candles. And an example is shown here of the Cepheid period luminosity relation, or Leavitt law, where every star on this diagram here is individually measured. You can measure the photometry of that star and its period specifically. You can measure the parallax to that object, and each measurement is directly relevant for this Leavitt law right here. Then we have another group of standard candles, which I would call statistical standard candles, because what we try to do is to measure a feature that is a part of a population, and the feature is not something you can measure on the individual stars, but you need the statistical sample in order to measure it. And so, of course, the tip of the giant branch is the most well-known of these, where essentially you try to measure the very steep decrease in the luminosity function shown here as this purple line. And I will be presenting elements of both of these types of standard candles. Among the stars that we use for this, among the individual classes, the most typical ones that are used are, of course, the classical Cepheids. Probably many of you here in this audience already know those, and those have enabled the most accurate measurements of the Hubble constant to date. Then there's, of course, other types of stars that are also pulsating stars that obey period luminosity relations or Leavitt laws, such as the Mira variables, and they're particularly interesting in the James Webb era. The RL-Lyrae stars are extremely good for more nearby things. And then there's, of course, other types of pulsating stars that can, in principle, be calibrated, but they do not offer the kind of calibration, the kind of accuracy that we need in order to measure the Hubble constant so accurately. And then among the statistical stellar candles, typically this is done in color magnitude diagram features. We have the tip of the giant branch. The real huge benefit, of course, of that method is that you can identify the TRGB in virtually any galaxy, and it already benefits from 30 years of usage for distance measurements. Then there's the sort of, let me call it, the exciting new kid on the block. These are the carbon-rich AGB stars, and of course, those are of particular importance for the James Webb era. And similar kind of to the RL-Lyrae stars among the individual standard candles, the red clump can be a useful statistical standard candle at shorter distances. So let me now very briefly summarize how we use stellar standard candles to calibrate the supernovae to measure the Hubble constant. It's a bit of a sequence of 2s here, but that of course derives from the fact that we use a distance ladder that requires these multiple steps. And so you probably know this diagram from the SHOES collaboration that shows sort of in one go the entire fit to this distance ladder. And of course, what we really want to do in order to measure the Hubble constant is map the isotropic expansion of space in the Hubble flow. And that requires going to very long distances. And of course, long distances mean that we need to use extremely intrinsically luminous objects, the supernovae, and you can see here how a supernova outshines its host galaxy. And that allows to then map the expansion of space. However, supernovae are really rare objects. So within a given volume, there's very few of them. And as a result, we have not measured a type 1a supernova in a galaxy to which we know the distance through geometric means. That means we require an additional step in order to calibrate the luminosity of the supernovae, which otherwise give us accurate relative distances. And we do this in galaxies that are close enough to detect the Cepheids and then to calibrate the luminosity of the supernovae by having distances coming from the Cepheids. And while the supernovae is, of course, very obvious in this image here as this bright white spot, we use the variability of the stars, the characteristic timescales and amplitudes and light curve shapes of Cepheids to identify hundreds of Cepheids typically per galaxy. And thanks to Henrietta Leavitt's work in the early 20th century, we know that the luminosity of these stars is proportional to the logarithm of the period. So basically, you need to measure the mean magnitude and the logarithm of the period, and you can go and start measuring distances. Of course, you do require the absolute calibration because for now this was just a proportionality, and the Gaia parallaxes that have been published over the last few years have been really transformative in this field, giving us access to hundreds of Cepheids with accurately measured parallaxes. And I'll say quite a few things about that. So in a way, what we're doing here is we're mapping the Hubble flow all the way back to a trigonometric scale provided by Gaia parallaxes or the other host galaxies to which geometric distances are available, notably the LMC and NGC 4258 with the megamaser. And with this distance ladder, of course, that's why we're all here. The Hubble constant accuracy has become so good that now we see a discrepancy with the early universe measurement coming from Planck. Now, the TRGB that I already measured does in principle does the same thing. It works just a little bit differently. Basically, what we want to do is we want to identify in this population of old red giants. This here is a plot from Friedman 2021. Here, I think this is many globular clusters in the Milky Way. So you want to identify where does this population of red giant stars end. Now, I will not go and tell you about the physics of these stars because I think we can deal with this from the point of view of just the empirical fact, because what we're trying to do is measure the absolute magnitude of this TRGB feature, and then we want to recognize that same feature in another galaxy. So this is the same thing as calibrating period luminosity relationship of Cepheids nearby, and then recognizing the same objects at another distance. And in this case, what gives us the distance modulus is the difference in the absolute magnitude calibrated and the apparent magnitude measured. And then, of course, in order to map the Hubble constant with TRGB, what we do is measure this for many galaxies that host type 1a supernovae, and then that sets the luminosity 0 point for the type 1a supernovae in the same way that the Cepheids will do this in the SHOES distance ladder. So I think everybody will agree that measuring the Hubble constant to 1% requires very tightly controlled systematics. And if I say anything that will have a consensus in the community, it's probably this one statement here. I would like to say one short thing on calibration and standardization, and I apologize if this is maybe a little bit semantic, but I noticed that quite a few discussions have often gone about this, and so I wanted to express a few thoughts on it. The first is that all standard candles require calibration and standardization, because calibration tells us what is the fiducial luminosity of an object. That's kind of like the platonic ideal of what it should be, but well, it does correspond to something we can actually quantify. And calibration also tells us how to standardize the measurements of the standard candles. Then the standardization is the process of making the observed samples match the fiducial. And that process is really the same for all the different standard candles. Now, if we work with the Leavitt law, typically what we have is that we have different luminosities of the sources. Those correlate, of course, with the period. And so what the calibration does is it sets the fiducial magnitude for a 10-day Cepheid at solar metallicity in a very specific combination of filter bands. Standardization then basically brings the luminosity of every star back to this 10-day fiducial, because of course you have large variations of period, but you can also standardize for metallicity differences. You can introduce corrections for time dilation and so on. And the really important thing is that all of these things are well calibrated and they're measurable either directly or by proxy. So this is really very powerful for the Cepheids. And furthermore, the scatter of the Leavitt law usefully constrains the uncertainties because every star individually is a standard candle. Then for the TRGB, we do have a fiducial magnitude, of course, and this is a statistically determined inflection point of a luminosity function that's populated by mixed red giant branch populations. And it's mostly used in the I band because this is where systematics, for example, due to the slope of the TRGB feature and the color magnitude diagram are minimal. Then on standardization, I think there's not yet really that much of a consensus because, for example, one group uses a metallicity correction and the other doesn't. Of course, you have age differences in the populations, and I think we're still working through some of those things. One of the aspects I've also focused on recently are algorithmic choices of how the TRGB is actually measured, and I'll say some things about that during this talk. So what does it mean to get the absolute calibration? Well, of course, what we need to measure mu, that's for the distance redshift relation, we require this absolute magnitude. And to this end, we use distance here. And I just mentioned here that this distance is in parsec because I will now discuss about Gaia and very nearby objects. So Gaia, of course, is absolutely wonderful, has brought us 1.8 billion stars with parallaxes and proper motions, and among those are many, many Cepheids and other stars that we may wish to use to measure distances. But it's also known that Gaia, on a global scale, so here you see the on-sky projection of Gaia, the Milky Way plane is whitened out here, and this map is based on quasar parallaxes. So quasars, of course, being extragalactic objects, should not exhibit any parallax. But if you look at the mean of this, as published in the Gaia DR3, you have an offset of about 17 microarc seconds. And then if you do a map over the sky, you see that there's actually quite a large amount of correlation, spatial correlation here, and this has been quantified by Lindgren et al. Using terms that are magnitude dependent, color dependent, and position dependent. However, a lot of work has still centered on figuring out just how good these corrections are, if the parallax bias has really been resolved as an issue. And so my postdoc Sanya Khan, shown here in the top right, has been doing work on using asteroseismology to figure out these parallax uncertainties. And so in asteroseismology, we use the eigenmodes of stochastically excited oscillations of red giant stars to essentially tell us what is the structure of the star. And Sanya had at her disposal 12,250 red giant stars. This is the largest sample to date with measured asteroseismic distances. And the way that this works is that you basically determine what is the bolometric absolute magnitude of these stars, which you then turn into a statement of parallax. And this uses stellar evolution models, spectroscopy, as well as photometry, and of course, the oscillation content of these stars. The best comparison for Gaia parallax systematics turns out to be afforded by red clump giants. That's because they are at a given magnitude, the brightest ones in our sample, but also because that allows us to do this all in a very homogeneous sample. And for this comparison, the systematics are of the order of 5 to 10 microarc seconds. And the real benefit of using this asteroseismic data is that it gives us dense locally dense, but an overall kind of patchy sky coverage of what this what these Gaia systematics look like. And this is important because, as you see here, these yellow points, the distribution of the physical pairs that inform the Lindgren corrections to the Gaia parallaxes, they're not really that densely sampled all over the sky. So having these dense, even though they're patchy regions, is actually really powerful at helping us get a better understanding of the parallax systematics. So if we focus on the initial Kepler field, I'll just point that out. That's this one over here. This, of course, is the best case for asteroseismology because we have uninterrupted multi-year, I think 4 or 5 years, time series for these stars. And that, of course, gives the best precision on the astroseismic frequencies. You can then look at, well, what is the parallax coming from Gaia EDR3, and what is the parallax that is determined from the astroseismic model? And you can look at this as a function of magnitude, and you see very clearly that there is a correlated residual here. So this is as it comes out of Gaia EDR3. And a lot of this can be explained by probably the gating mechanisms involved and so on. That, I mean, the part about having this correlation that is so magnitude dependent, this correlates very strongly with things like the gates and the changes of the way that the stars are followed or tracked in Gaia. Now, if you apply the Lindgren corrections here, you will see that in this magnitude range between 11 and 13, the parallax offset is essentially 0. So there's no residual parallax offset here. However, it comes at the cost of a residual parallax offset at the bright magnitudes, which was 0 prior to doing that correction. And thanks to the sky coverage that we have from the asteroseismology, we can then do this for different regions. So the blue here, for example, is the test field. Red is Kepler. Yellow is the band along the ecliptic plane I showed earlier. And this is comparing our results with other results of this parallax offset in the literature. And I think the most relevant thing or most important takeaway from this plot is that this offset is not simply a function of magnitude. So there had been some earlier indications that maybe this here would be just a clean trend as a function of magnitude. But the TESS observations here, they're processed the exact same way as Kepler and K2. And there's no way that these can be reconciled with one another. So it seems very clear that at the bright magnitudes, we don't sufficiently understand the parallax offset to get things very accurately. But at fainter magnitudes, and here I'm saying, well, 11 and fainter, it looks like even with Kepler, we see essentially a 0 parallax offset. We also measured this with Cepheids, well, with the cluster member stars of Cepheid hosting clusters. We also saw this. And from K2, we have some indication that it's close there, but the K2 is unfortunately a little bit noisy. So what this means is essentially the yellow points that are shown here on the sky map, those are the physical pairs that inform the parallax offset of the bright sources. And it seems that the sampling of the full sky is not sufficient at these bright magnitudes. But at the fainter magnitudes, that is actually the case because the fainter magnitudes have been more mapped in more detail. So let's now move to how we use Gaia parallaxes to calibrate the Cepheids. And in fact, to do this in this sweet spot of parallax where the parallax offset is either small or 0. And so my PhD student, Mauricio Cruz Reyes, who's shown here at the top right, had a paper that came out earlier this year where we were able to get a 0.9% calibration of the Cepheid luminosity scale. And we approached this by mining the Gaia database for clusters that exist in the vicinity of Cepheids. And so to give you an idea of what a star cluster looks like, here we have an example of one such open cluster. Of course, you have foreground and background contamination, but thanks to Gaia, we actually have information both on the position of the objects, but also in the way that objects move. Here are the proper motion axes, and you see very clearly how the cluster is kinematically distinct from the background population. And so using this multidimensional membership analysis, we can very nicely isolate the main sequence in this cluster, and the Cepheid is shown up here for this particular cluster. Now, the cluster parallaxes are extremely useful because they combine two very useful things. One is they benefit from greater precision because we can average over a large number of stars. And so the statistical precision, of course, improves the square root n, although there is angular covariance that we do take into account. But that angular covariance is also very well calibrated, and the systematics of the measurement are actually easier for these non-variable fainter sources. So that allows us to get very, very good cluster average parallaxes. And we do this for 34 Cepheids that reside in 28 clusters and obtain a typical error that's only 7 microarcseconds. And that's really, really tiny. So to give you a sense of scale, this is a small coin on the surface of the moon observed from the Earth. So with this in hand, we can then do a combined fit of the 26 cluster Cepheids and 225 field Cepheids, and this allowed us to measure the residual parallax offset for the 225 field Cepheids while also calibrating the absolute Leavitt law in the Milky Way to better than 0.9% in distance. And with Gaia DR4, we project that we would be able to get to about 0.4% thanks to the improved proper motions that will give us more and better parallax parameters. So why are cluster parallaxes really so good? I mentioned this briefly earlier, but essentially this is because Cepheids are bright, and this is a plot from Adam Rees's paper that shows the number of stars as a function of magnitude that were used to inform the Lindegren corrections. Here in blue, we see the bright end where the Cepheids are located, so the field Cepheids would fall in this category. But the Cepheid cluster stars, so these member stars, they really fall in a region where many, many objects were available from the LMC and also at even fainter magnitudes from the QSOs to calibrate this cluster offset. And so this is really behind the zero or almost zero residual parallax offset that we find in this magnitude range. Now, we did not use the LMC in this calibration of the Milky Way Leavitt law, but we did use the LMC as a cross-check just to make sure that, in fact, the cluster stars are consistent with zero residual offset, and we find a consistent answer for this. So using these cluster Cepheids then allows us to actually improve the Hubble constant measurement, and it turns out that this grows the Hubble tension. So with HST infrared photometry from Adam Rees's paper, these cluster Cepheids basically exhibit an LMC-like dispersion of only 0.07 magnitudes. This is really unprecedented. We've never had such an accurate calibration of the Leavitt law in the Milky Way, here measured with the parallaxes of these clusters. And because of the small uncertainties on the parallaxes, we basically have the same weight for one cluster Cepheid as would otherwise be contributed by 9 field Cepheids. And one thing I'd like to just point out is that the astrometric analysis of the clusters in Rees et al. Was done by a different team and using different stars compared to what Mauricio and I did. And so we get very similar results, but there is an average parallax difference of 5 microarcseconds. But just to show that two different teams doing the same analysis come to comparable conclusions. Now, combining the absolute magnitude that is derived based on this fit with the analysis by the Shoes team, this leads to an H0 of 73.11 or so, represents a 7% uncertainty reduction compared to what was available before, and would increase the tension from 5.0 to 5.3 sigma. So these cluster Cepheids really are very useful for calibrating the Leavitt law, and with more such clusters in hand from Gaia DR4, we expect to go to about a 0.4% calibration in the Milky Way. Now, of course, the James Webb Space Telescope has been an enormous success already, despite its short lifetime, and everybody's extremely excited to see the results coming from this new space telescope. Since Adam will be presenting a talk here soon, I will actually just say a few words on it and leave it to him to describe the work that he led. So here's the reference to his paper, but I did want to do a quick shout out since I mentioned it in the abstract. It's just absolutely phenomenal how the better spatial resolution of James Webb allows for better photometry to be measured on these Cepheids. So you see here the comparison of the HST infrared measurements in H-band and the closest analog that we have in James Webb. That is about a 4 times better spatial resolution, whereas the James Webb spatial resolution is even slightly better than the optical HST resolution. And of course, this means that we have better source separation, meaning that there's lower uncertainty coming from the crowding correction. And the synergy between HST and James Webb is really great here, because combining the optical from HST and the infrared from James Webb really does the entire measurement then using observations that use similar spatial resolution. Quick spoiler alert, crowding is not at the heart of the Hubble tension, but I'll leave it to Adam to say more about that here in this talk series. So now let's get to the tip of the red giant branch. I promised that I would be speaking about this. So in particular, this will have a little bit of overlap with what Dan Skolnick presented a couple of weeks, or now maybe a couple of months ago, as well as work of mine that is currently under review and in preparation. So just as a reminder, the TRGB is a statistical feature that relates to the drop-off in the luminosity function. So this is just the number of stars as you go to brighter magnitudes. That's what you see here. You have the actually binned luminosity function shown here as this wiggly line, and then a smooth version of it in purple. The TRGB measurement itself is done in this case using so-called Sobel filter. The Sobel filter is a numerical way of calculating the derivative, and the mode of this so-called edge detection response, here shown in red, is the value that sets the TRGB measurement. This is going to be important for what I will be speaking about. And so, of course, the way I approach this is coming to the TRGB was a bit of a new thing for me, but of course we see this early and late universe tension, and then there was a measurement of the TRGB that fell sort of in between this, and the question is, well, why does it do that? Is there something that we can do to help improve the measurement, and with that reconcile these measurements? And as I started looking at this, the very first thing I noticed is that near the tip of the red giant branch, all the stars are measurably variable in the Large Magellanic Cloud. So here we have a color magnitude diagram. This is the de-extincted I-band magnitude and the D-red in color. The contour here is just a visual guide. Actually, all the stars are shown at lower transparency here. The TRGB feature is roughly indicated by this dotted line, and the color scale here is the fraction of stars that have been reported as the so-called small amplitude red giant stars in the Ogle catalog in each bin, 2D bin here in the color magnitude diagram. And you see how this number increases to about 100%, but you can see it perhaps even better when you look at the luminosity functions. Here, the black line is all the stars. The orangish line here, that's the Ozarks. So these are the small amplitude red giant stars, and you see how it goes to 100% really at the tip of the red giant branch. And then the gray line is just the stars that are not Ozarks in this magnitude range. So this already was quite surprising. But then when we look at actually the period and luminosity of these Ozarks, we see many different sequences. And this is known, this has been known for more than 20 years, that there are many such types of sequences. But what's quite striking is that you see by eye very nicely the tip of the red giant branch feature in these sequences. And so the question that we asked was, well, would this allow us to get a better measurement of the TRGB feature? Because this, of course, is what we need to measure the Hubble constant accurately. And so in what follows, I will be basically talking mostly about the Ozarks group. And I drew this big box here around it to illustrate that Ozarks uses all these stars, which also means that it uses all the stars at the TRGB feature. There's no selection of stars because 100% are variable at the tip. Then the A and the B sequence, these are specific period luminosity sequences that are characterized by low overtone pulsations. and make up the bulk of the Ozark stars. And I just introduced this because these are the two most populated ones, and I was interested to see if they would give similar results. So what's very interesting is that the variability of these sources actually identifies the age of the population. And so I have responded to the referee on this paper almost 2 months ago, hoping to get a response soon. But I'll show you a small preview here of what is in the new version, and that is using ages that were determined using spectroscopy by Povik et al. We are able to show that the B sequence, that's this one here, is populated by older stars than the A sequence, and you see the histograms over here. And it's kind of it's commonly adopted that the older red giant stars will give you the more reliable result on distances, because there's less variation of the TRGB magnitude in stellar models for older stellar populations. So in a way, the B sequence, if you can isolate it using the variability, it automatically gives you the population that is most desirable for measuring the tip of the red giant branch feature. Now, a small caveat here, because the amplitudes of these variations are very small. We're talking somewhere between 0.01 to 0.04 magnitudes. This is really not very much, and the use of these kinds of variations is currently limited to very nearby objects that have been measured a lot. But I think that thanks to this variability, we can better understand how the measurement works, and this, of course, we can then use at longer distances as well. One thing that we focused on quite a bit is smoothing. So smoothing is required in order to get a good estimation of this inflection point of the luminosity function. I'm showing here as this raggedy line, that's just the binned luminosity function. And then it's common practice to apply some sort of smoothing, usually done by a Gaussian weighted kernel, along this luminosity function to get something that is more easily differentiable. And that actually gives better signal to noise. So in some sense, the more you smooth, the better signal to noise you have. But, and this is a big caveat, you introduce wider and wider correlation among the bins of your luminosity function, and that is something to take quite seriously. So when we looked at this both from the observations and from simulations, here basically we reproduced using an analytical model. We reproduced the luminosity function, and then we're able to scale things up and down to do some tests and simulations. What we find is a very strong dependence of the measurement of the TRGB as a function of the smoothing parameter that is employed to increase the signal to noise. And this is, of course, not the first time that this was seen. To me, it was striking nonetheless, and I wondered, well, how do we set an objective criterion for deciding which level of smoothing to use? Because if you look at this blue dots here, this is if you use all the red giant stars in the sample. I mean, ideally, you wouldn't want any smoothing. You would just use the luminosity function, but that obviously increases, that has very high error, and it also doesn't seem to be the best measurement in the first place. There's also bias here in the center value. So how do you select really a good value for sigma s? And what we decided is, well, what we want is to be insensitive to the choice of smoothing, and insensitivity to this choice basically means that you want a small derivative relative to the value of sigma s that you choose. And so we said, well, we identify the range where our output measured magnitude is stable with respect to the choice of smoothing parameter. And we just arbitrarily said, well, let's take 0.1 for this measurement. And what this gives is, for the black and the blue, roughly the same measurement in the end. They're consistent to within the errors. We also were able to then look at, well, how does this bias, for example, depend on the contrast? Contrast here is the number of stars above and below the tip, or W is the inverse steepness of this feature. So we could use our simulations to quantify these things as well. So then if we choose the smoothing scale accordingly, what we find is that we have, well, the black points here, these are the Ozarks. So again, the full sample of the stars. We have the A sequence here in yellow and the B sequence here in red. You already see that these lines are not at the same magnitude for the TRGB. So what we see is that the B sequence and the A sequence give significantly different apparent magnitudes in the LMC, and the ozargs are kind of in between, which is maybe not unexpected given that the ozargs contain the A and the B sequence, and in fact, A and B are the most populated in the sample. And then the blue points here is using the exact same definition for how we choose the smoothing parameter and so on, but using all the red giant stars. So this leads to a consistent result with the ozargs, which is also what you expect, given that the ozargs make up 100% of the stars at the TRGB feature. So this gives us an opportunity now to compare these different sequences, and I tentatively refer to these things currently as the twigs of the red giant branch, because of course you have a tree with branches, and the smaller, finer details become the twigs. So the A and the B sequence then would be these sort of finer details. And in this diagram here, you see the color magnitude diagram on the left of the regular AGB population. Then here in this second from the left panel, we see the A sequence and the B sequence in red and yellow, and then a portion of the ozargs in black. And here we see the luminosity functions that are markedly different between the B sequence, which is more skewed and more peaked towards the tip, than, for example, the A sequence shown here in yellow. And really, we find significantly different answers for the A and B sequence at 4.5 sigma significance, depending on the filter. But overall, using the overall ozarg sample, we find the most precise calibration of, or measurement of, the apparent magnitude of the tip of the red giant branch in the LMC. So I think what's really important here is that the variability allows us to understand the makeup of this diverse stellar population, and we shouldn't ignore this kind of diversity going forward. So right, I already said that this is the most precise calibration to date, thanks to these small uncertainties, but it's also consistent with 3 independent calibrations of the TRGB that do not use the LMC at all. For example, there's a recent calibration by Lee et al. In AGC 4258. There's the extragalactic distance database calibration that uses a metallicity term to calibrate the TRGB by Ritzi et al. Has been very widely used. And then the Gaia parallaxes that were used in a maximum likelihood analysis also by Lee et al. Those are all fully consistent with our results. And as I mentioned previously, all the stars at the tip are ozargs, so this is applicable to the Hubble constant. However, the variability of the sources being so small, it doesn't really affect the mean magnitudes at the tip. However, it does allow us to do further investigations. And one thing that we're doing at the moment with a student who recently began his graduate studies, Nolan Koblischke, who was the second author on the paper I mentioned earlier, is that we're using these twigs in the SMC now to compare the 2 populations. And I'm happy to share with you, for example, this plot here on the right, which shows that all the stars at the tip of the red giant branch are ozargs also in the SMC. So this is not a fluke that is somehow just one galaxy where this is the case. This really is due to the evolutionary sequence in which stars progress through these PL relations as they get older. And now I'd like to briefly get to connecting this with what Dan spoke about with respect to the CATS algorithm. So those of you who did not follow that presentation, essentially there's a push to standardize a TRGB measurement. And Wu et al., Jeshi Wu et al. Looked at many fields of the same galaxy here from the GHOST survey and considered the magnitude of the TRGB that was returned for each of these fields as a function of this contrast ratio here. So the ratio R is the ratio between the stars above and below the tip. And this is, of course, measurable from the population directly. And when compared to the residual of the median of all these fields, what was found was a very clean 5 sigma detection of a slope in this tip contrast relation. And so the CATS team then have been using this calibration in order to standardize the TRGB distances. And when also introducing the Pantheon plus supernovae type 1a sample and a consistent measurement that uses the standardization technique for all the different galaxies. There's additional algorithmic choices I don't have time to get into, but once this is all done, then the value of 73.2 plus or minus 2 kilometers per second per megaparsec comes out. So with this standardization technique, the Hubble constant found using a TRGB measurement is fully consistent with the Cepheids and not really that consistent with Planck. So I've been trying to understand what's been going on this end, and in the revised version of our paper that's currently under review, we have some answers about that. And just to be a little bit technical, I'd like to explain what we've been doing here. So I mentioned that we use a Sobel filter for doing the measurement, and this, but in reality, what people usually call this is the edge detection response, or EDR, and the tip of the giant branch magnitude is simply the mode, the highest point in the EDR. Now, the EDR can be based on different combinations of measurements, and what we used in our paper is the unweighted Sobel filter. So here, the EDR is simply the output of the Sobel filter, which is this derivative of the bin above and below the bin of interest. But you can also introduce a so-called Poisson or inverse Poisson weighting, which essentially just divides the Sobel filter by the square root of the number of sources in the bins considered, basically saying this would be the Poisson noise. So this gives you a sense of signal to noise. And I believe that this approach was championed by Barry Medor, who's in the audience. And then, of course, we have another one that has been considered as seems to be referred to as signal to noise weighting, where the Sobel filter output is weighted by essentially the Poisson weighting. So it turns out that this is about the same thing as doing the Sobel filter square divided by the square root. And I'm not too sure why one would go about doing it this way, but I have seen this in the literature. So the problem one that I see in this approach is that a signal to noise statement becomes difficult to interpret because of the correlation among the magnitude bins that's introduced by the Gaussian smoothing that is being done. So in a way, I'm not too sure how accurate when using these smooth luminosity functions this would be. The second and more worrisome point is that the weighting of the Sobel filter output shifts the mode of the edge detection response, and that actually ends up creating this tip contrast relation that was found purely empirically by the CADS team. And so to illustrate this, here we have, based on the simulations from our paper, we have the difference in the TRGB magnitude as a function of the contrast. And this is all based on the same set of synthetic luminosity functions. And you may wonder, well, why is the contrast different? And in fact, it's different because the contrast is measured relative to the TRGB magnitude. And so since the TRGB magnitude shifts, so does the contrast. So in other words, you find higher contrast values when using this Poisson weighting, but you also see a fairly strong, in this case, nonlinear relation of the contrast to the tip of the red giant branch bias. And this, among the sort of lower contrast ratios that were also in the CATS paper, I'm showing here just for comparison the slope of that was found by the CATS team. This is quite consistent with what we see here from the simulations. If we use this signal to noise weighting, we find something intermediate. And if we use the unweighted Sobel, we actually don't see any bias at all. But also the contrasts are smaller. So it's perhaps not surprising that the signal to noise Sobel falls in between these two, given that it takes the square of the unweighted Sobel. So this leads us to think that we really should not be using the weighting using the Poisson error because it introduces this tip contrast relation. However, once we use the Poisson weights, then of course we have to standardize and we have to correct for the tip contrast relation, just like it's done in the CATS analysis. And so the baseline, the bottom line here is, if you're using weighted Sobel filters, you have to do standardization. If you do unweighted Sobel filters, you can get away without that. So a few conclusions, because I think my time is coming to an end. Some conclusions on the stellar standard candles. I spoke to you about Gaia, and I think the most important take home is that if you're using Gaia parallaxes, then you have to figure out the residual 0-point offset that applies to your sample under study self-consistently with your study. Using measurements of that 0-point offset based on other parameters can only be done if you really understand whether they're fully applicable. But what we do see is that there's essentially no residual offset at fainter magnitudes after the Lindgren corrections have been applied. And this is certainly the case near the galactic plane where these globular clusters, open cluster stars, were located. Now, for the Cepheids, what I would like you to take away is that the Milky Way cluster Cepheids are really the most promising route to getting to a 1% Hubble constant measurement, because they will allow us to calibrate the Levitt law to about 0.4% or so in the future. And of course, with James Webb, we have an exciting new toy to get extremely precise photometry with much lower uncertainties due to crowding. Now, with the TRGB, the things that I wanted you to take away is that the diversity inside the population is quite difficult to control, but the variability will allow us to dig deeper into this to understand which of the stars are really the old ones and hopefully make some progress on the method. Depending on choices of how, whether weighting is applied or smoothing and so on, one can easily get differences at the level of 3 to 5%. And using our Ozargs and our objective way of choosing the smoothing scale, we managed to get the best LMC calibration to date. Now, usefully, this CATS algorithm really seeks the objectivity and standardizes for the tip contrast relation. And so I think this is the way to go when you're using weighted Sobel filters. But all that said, I think what we also really want is more cross-checks among stellar standard candles, because this, in the end, will help us improve these methods and eventually get to the most accurate Hubble constant. Now, some conclusions on the Hubble constant. I mentioned the cluster Cepheids are extremely useful. We're also working on other systematics of Cepheids. And for example, we have some work that looks at the stellar association bias I didn't have time to talk about today. But I think with all of this, we will get to 1% and not such a distant future. Then the diversity population of the TRGB should really not be ignored. Once that is combined with a consistent treatment of Pantheon Plus, the result is, I seem to have a number issue here, but apologies, it's about 73, fully consistent with late indicating here the shoes result. If we apply our LMC calibration to the CCHP results, then we would get to something like 71.8. But I realized that this is not the most important comparison because of the methodological differences in the TRGB measurement. And so here I would say this is a useful indicator that our calibration supports a higher value of the Hubble constant, but really, I think the fully consistent way of measuring H0 using a consistent methodology applied to all the host and anchor galaxies at the same time is the more important result here. Now with James Webb, this will really improve the uncertainties. And basically, once the TRGB moves to a higher value of H0, then there's not really any disagreement anymore among the late universe probes, at least not among the ones that have a really high level of precision. One thing I did quickly want to mention is that K corrections actually become relevant if we seek to go to a 1% measurement with the TRGB using single filter James Webb Space Telescope measurements. Obviously, didn't have time to mention this today here, but a paper of mine from last year will tell you more about that. Thanks very much for your attention.
Thank you, Richard, for the great talk. And do you have any questions?
Yeah, a great talk. The twig stuff is just beautiful, and I feel like really meaningful. So the piece of like the H0 story that I'm not sure how it will work out is you have now this new information from measuring periods, but then for like galaxies in the third rung of the distance ladder, I don't know if that's possible. So like, what's then the path of like utilizing this to do a full H0 kind of ladder?
I think So this will not translate directly into the H0 ladder. This is going to be, maybe as an analogy, I would say this is more like understanding the metallicity effect on Cepheids. You can't immediately measure spectroscopy of very distant Cepheids, but you can use the information that you obtain where you can measure it to then correct the measurements later. So here, what we're seeing is, and I don't want to give away too much from Nolan's paper that he's currently preparing, but we are seeing that, for example, this metallicity correction that is applied by the RITSI EDD team, so the RITSI calibration, that this seems to be warranted just from the point of view of how the variability among ozarks changes between the LMC and the SMC. So even among the old red giant population on the B sequence, we do see a significant shift in period and as well as magnitude and color. And so this really seems to be an indication that this metallicity correction is needed to get to the highest accuracy.
Thank you. There is a question in the chat, more than one, actually. I don't know if you can read them.
So Deep says the A and B sequence,
And
since the A sequence is less than, come again?
There is the Barry one before.
Oh, sorry, I didn't see that. I don't have the full chat window. Oh, okay, here. Barry's question. Would you care to share your thoughts on the role of the very large ground-based telescopes in bolstering up the local zero-point calibrations on the extragalactic distance scale? That is a great question. And I wonder, because I guess I suppose you're referring to things like the ELT and the TMT and the GMT. It will all boil down to access to these telescopes, I think. And of course, it would be fantastic to have the spatial resolution and the light collecting power of these instruments. But in particular for the ELT that I'm a bit more familiar with, what I'm concerned about is the stability of the PSF over long timescales, because the focal plane is constantly changing and because the AO system has to, work. And so I don't know how good this will be, but it's something that interests me a lot. So I'd be happy to hear your thoughts on the matter as well. The other point is, of course, that collecting time series from the ground will face extreme competition from other PIs wanting to get time on these large facilities. But I suppose that with the GMT, perhaps the Carnegie Institution will have rapid access, I hope. Also,
there is the deep one, the A plus B sequences. I don't know if you can read it.
In fact, there's an evolutionary paradigm that describes how stars will, as they will move towards the TRGB on the red giant branch, how they will jump between these sequences when you consider P1 the period of the dominant mode. And so essentially, you see this here, that you have a significant age gradient on sequence A that moves from the left to the right, so from shorter to longer period. So the stars essentially will climb towards the TRGB and then eventually jump over. But it's not so clear exactly when they will do this. And you have stars here, these black ones, these black points, for example. These are also technically on the A sequence, because we cannot distinguish here just from the PL sequences between stars that are on the RGB versus the AGB. So it's a little bit difficult to separate this in terms of evolutionary stage. But what you certainly can do is select the older stellar population by focusing on the B sequence. Does that answer your question? Not sure. Of course, the LMC has a continuous star formation, so you have stars of all ages populating the RGB.
Okay, yeah. Can you hear me?
Yep.
Yeah. So that maybe answers my question, but yeah, I'm just looking at this age distribution for the H sequence, and I see you measure a fainter tip for it by 0.1 magnitudes, but that's not really it's not really a tip of the RGB, right? Because the star hasn't climbed all the way up to the TRGB. So I think it's just maybe a language miscommunication Yeah.
Yeah, I think this is it. Although you do expect a fainter tip for younger stars. I mean, you have those would then have higher mass, right? And they would reach the TRGB at a younger age. So what constitutes the tip is then probably a bit tricky to differentiate. But the way I approached it here was that I didn't want to necessarily really go at this too much from an astrophysical model point of view, but rather from an empirical point of view of what contributes to the TRGB measurement that is made, right? And these two sequences are the dominant part of what we usually would look at when we try to measure the TRGB feature. And yet, we can distinguish an age between those two. And for example, the older stellar population gives us the more luminous tip, just as expected. But I think we can really learn a lot more from this variability. Then what really constitutes a tip is indeed very tricky. And also assigning the star moving upwards towards the tip or downwards from the tip, or ones that are already in the AGB stage, that's extremely hard. But because these stars are multi-periodic, you actually have 3 different periods reported for all of these in the OGLE catalog. You may be able to do more, and you may be able to go quite a lot deeper in this, but we're only at the beginning of really understanding how these ozargs can improve the TRGB measurement.
Okay. Yeah. Thanks. I guess the other follow-up to that is, if when you look at the supernova host, right, you typically aim in the stellar halos, and we don't expect 2, 3, 4 gigayear-old stars there. So I guess the other comment / question is how that's related to the applicability of this in the distance ladder and the further rungs of the distance ladder.
Exactly, but there I think the answer is that if you know that the outer halos of these supernova host galaxies are populated by old stars, then you do not want to have the contribution of the A sequence. And so then you can use in the local universe, you can then use for the galaxies where you can measure this, you can use the old population given by B sequence to calibrate your absolute magnitude. So then you get rid of the young stars, and then you're comparing old stellar populations to old stellar populations, and that improves the homogeneity of your measurement.
Okay, thank you. That clicked for me now.
Okay, thanks.
Thank you so much.
Bye-bye.